Today we're going to continue our theme of linkage folding, but we're going to generalize our notion of linkage. And so we want to go beyond folding just one-dimensional structures in 2 dimensions, which is what we've been talking about the last 2 classes for the most part. We did a little bit in 3D. But Carpenter's rule theorem is about unfolding these things. We talked about locked trees when you add degree 3 vertices here. I want to make things a little harder and more interesting by adding fat objects to those edges. So these are solid regions. Think of them as polygons, but they could also be smooth, whatever, splines, circles, whatever you want. They're still hinged at points, and they still fold kind of like this underlying linkage. But now the collision constraint is even worse. Not only are the bars not allowed to touch, but these blobs that are attached to the bars are not allowed to cross each other. Question?
Isn't it kind of like a rigid sub-linkage?
Yeah, it's kind of like say this was a polygon, because everything's almost a polygon. Everything's linear to the first order. So you could just like triangulate this guy and say, yeah, that's just like a more complicated linkage. Now this moves as a rigid object, and it can't collide with anything else. You can even overbrace it if you want, add lots of bars, but it will move the same. Of course, then you have collision, so that's kind of cheating. But if you triangulate, you will get the same behavior as these rigid objects. Yeah. Now we know that as soon as you have a vertex of degree more than 2, things can lock. So it's no surprise that these things can lock. What's surprising is that you can prove interesting things about them not locking. Let's start with some simple examples of them locking. So these are triangles hinged together at points that are locked. And this field began back in '98. This is when we were working on locked trees. Marty, our cameraman, was working on locking triangles. And like after a day, he came up with these examples. They're not too hard to find. This is probably the most compelling one. You have on the top those obtuse triangles, and because they sort of share an edge like that, they can really only hinge one way. They can only close this angle. They can't open it. And so this guy's stuck. Can't get out. This is a little trickier, but what's interesting about this example is all the triangles are equilateral, which is pretty special. If you were hoping for some good result here, you think, well, equilateral triangles, those are like the simplest nice shapes I know. So maybe they work, but they don't work. They can lock. This may be a little less obvious, but because this guy's reaching around on the top, can't unwind if this is drawn sufficiently tight. And in fact, it's pretty obvious because we could apply rule 1 right here. Right? It's an edge spanned by 2 acute angles, so that glues in there. Then you have a rigid triangle here, so that stays collinear, and then you're screwed. Then the only thing that could move is that top triangle, and it can't get out. So the self-touching version is rigid, and therefore any perturbation is strongly locked. So we can use the same tools we did, because you can ignore the fact that these are solid things and just think of them as triangles as linkages, and we can still use rules 1 and 2 and rigidity and strongly locked and all those good things and prove that these things are locked. And we'll do that some later. But I claim it's useful to think about rigid shapes being attached to bars. Because in particular, well, we know how to unfold things like this. So maybe there are certain kinds of shapes that you could attach. Maybe if I just thickened it a little bit, maybe that wouldn't matter too much. Maybe if we know that if you add equilateral triangles, that can lock. But what if I add some very small, thin triangles to these edges? Well, then it turns out you can't lock for the appropriate definition of thin. So this is the idea of an adorned chain. Where you have rigid shapes attached to bars. So the bars kind of guide the motion. We're going to think about the underlying linkage, the underlying chain here, and then there are these rigid shapes attached to them. They come along for the ride. And in particular, yeah, blah, blah, blah. All right, we have some terminology. An adornment in general looks something like this. This is rigid region. But it has this segment marked on it called the base. The rest is the shape. Okay, so as the bar moves, you just rigidly move the shape so that the base lines up with the bar. And that's how they follow along. And now we can define the notion of thin, except we call it slender. A little nicer. Best thing about mathematics is you get to make up terminology. Not the best thing, but a cool thing. Yeah. At some point, my dad was having dinner with a group and saying, yeah, that's great. You know, we've made up all these fun words like slender and ununfoldable, which is something we'll talk about. It's like, what words have you guys made up? And one guy raised his hand and said, oh, Ethernet. So, we're not that cool. All right. So what does slender adornment mean? It's going to be shapes more like these thin things, maybe even these, I think, but not so much this. That doesn't look so slender to me. What we're going to do is walk along the boundary from one base endpoint to the other. So maybe draw an example here. I think that'll be slender. So we start here, we walk along in this direction. And what we want is that this motion, as you walk along there, you monotonically increase your distance to the endpoint you started at, the former endpoint. And also sort of equivalently, you decrease the distance to the other endpoint, the one you're approaching. And this should be true no matter how you get there. So I'm walking along this outer boundary, and I'm looking, what is the distance to this endpoint? I can just draw a whole bunch of concentric circles around that point. As long as these circles only hit my curve once, I'm happy. That means this distance is increasing monotonically. Okay, but you should also draw them from the other side. It's like offset curves, good old straight skeleton stuff. And lo and behold, you monotonically move outward from here if you went this direction, outward from here if you went that direction. And this should be true for both sides of the curve. This one looks like, yeah, monotonically increases distance from here, decreases from there as you move right to left. That's slender. Pretty simple definition. The biggest slender shape you could hope for, the biggest one that you can do, is if you draw one giant circle centered at each of the points, passing through the other endpoint. That's slender. I know it looks pretty fat. This is like a rouleau triangle. But that's still slender. And if you go outside that, you're in trouble. Then you won't be monotonic. If I went here and came back, then I'm getting farther away, but then I'm getting closer again to this point. So that's not allowed. Cool. So that's slender adornments. There's actually a couple different ways to define it. And yeah, question. Yes. So I don't mean to say that if you take any, you can fit an equilateral triangle in there, I think. Well, like this. So equilateral triangle is not slender. We can check that. I know it's weird. It's not a monotone definition. If you take a subset of your slender shape, the result will not necessarily be slender. So if we do equilateral, if you draw a circle, there's a circle here that's going to kiss this edge. It's centered here, and it kisses this edge of the triangle. So that means you're going out and then coming back, getting closer again. So equilateral triangle is not slender. That's good because we know equilateral triangles can lock. So better not be slender, because I'm going to say that slender chains cannot lock. That's what we're going to prove. All right, let me give you another definition. It's a little bit easier to work with, and also give some intuition about why slender things are good. Well, it will give some intuition, not immediately. If you look at inward normals from the shape, then they hit the base. Whatever. This is sort of assuming that my shape is somewhat smooth, but it's not a big deal. So let me take a nice shape again. If I look, here's a tangent, here's an inward normal. I extend it, it hits the base. All of these inward normals hit the base. That's good. In this case, I could take an inward normal from here, say, if you don't want to do the corner because it's a little confusing, and you will go out here. You don't hit the base. You hit this line, of course, unless you happen to be parallel. You'll hit the line, but I want it to actually hit the line segment that is the base of the shape. And maybe go back up here. The Rouleau triangle. You take one of the inward normals here, it will actually just barely hit the base. It hits it at a vertex. That's okay. This is slender. But that's why if you went a little bit outside, then you'd have an inward normal that doesn't hit the base. So it's pretty easy, given a shape, to tell whether it is slender. Just draw a bunch of inward normals, and either works or it doesn't. If you make some complex thing like that, that's not going to be slender. Now, you could take something called the slender hull. I'll define that in a moment. Here's another definition. It's a union of half lenses. Half lenses I want to define sort of like this Rouleau triangle example. But I don't necessarily take these vertices as the center. I take some vertex here as the center. I draw some, let's say I take two of them, and I draw a circle centered here passing through here. So that's like this. Circle centered here passing through here. That's like this. I'm getting better at drawing circles. That's a half lens. If I drew the whole thing, that would be a lens. Okay, and so you get a choice. Now I could maybe choose this point, and draw a circle here, and then there's another half lens. I just take a whole bunch of those, union them together. That will always be slender. That's kind of obvious because you look at any of these inward normals, they're going to hit one of these x's that you drew on the line. What's a little less obvious is that every slender shape can be made by a bunch of these things. Now, admittedly, possibly infinitely many of them. If my shape, so for one of my favorite slender shapes, is a right triangle. Okay, and you can check all the inward normals, hit the base. Here, they just barely hit the base. Obviously, you need an infinite, all of these half lenses are curved. But if you take an appropriate infinite number of them, namely, all the points here, there is a lens that covers it. You just take all of those. I'm not drawing them perfectly, but they'll look something like that. You take the union of all of those, that'll give you the triangle. So in fact, any shape you want to make slender, you take the lens that hits every point. So this is sort of the slender hull. If you have some shape that's not slender, this is really ugly. There are inward normals that go up. But I can sort of fill it in. I don't know exactly what this will look like. But for example, this point is kind of bad. It's got an inward normal going up. So I'll take the slender hull, I'll take some. Did I lie? Can I do that? I think it's even simpler. Let me check. Yeah, I was more complicated than I have to be for half lenses. This does work. It'll still be slender, but you can be. In fact, because you need to be monotonic the whole way around, you might as well always use these 2 points as centers. It's been a while since I've seen this stuff. So if I had some point like this, it'd be a little bit nicer if I took circle centered here and circle centered way over there. So it's almost vertical. That's also a half lens. That'll be smaller. I can, of course, add more stuff later. But that's sort of the minimum you can get away with, is that half lens. If I want to add this point, it's going to be something like that. Circle centered here and here. And that's my half lens. All right, so that actually uniquely defines what you want to do here, which is you take a circle centered at this point, you take a circle centered at this point, and you add that to your shape. And so in general, it's in this example, it's going to like fill in something like that. This might be okay. It might fill in a little bit here. It's going to fill in something. So then this shape will be slender. So if you have some shape that's not quite slender and it's messy and ugly, you could fill it in like this. And as long as that fill-in doesn't intersect with any other shapes, you're still okay. So if you have some crazy collection of shapes, you fill them in with the slender hull, and they're still not self-intersecting, then you know that thing will not be locked. And of course, if the fill-in doesn't intersect and you can move it without intersection, then the original thing won't intersect. So that's good. Now, of course, if you have crazy interlocked shapes, well, those are going to be locked. So you're in trouble. Something like this. And then when you take the slender hull, you'll see, oh, they're overlapped. So I don't know what's going to happen. Of course, we're not going to be able to characterize every collection of shapes that lock, but slender gives you a pretty good idea of when they do. When you're safe, when you're guaranteed safe. Oh, I think I even have a figure of a whole bunch of slender things. On the top, we have mostly lenses. Actually, symmetric. They're all symmetric. In this case, I took lenses, not half lenses, but you could just take the upper half or the bottom half. You can take regular kagons, circles, half circles, rouleau triangles, various combinations thereof. Lots of shapes are slender. You can take this on one side and this on the other side of the edge, whatever you want, or just put an adornment on one side. Many things are slender. So we want to prove if you have a slender chain, you are not locked. That's the theorem from, I guess, 2006 originally. The journal version just appeared. And the way we're going to prove that, as you might guess, is using the Carpenter's rule theorem. We have this underlying chain. We know how to unfold that. Maybe, if we're lucky, slender adornments won't mess up the Carpenter's rule motion. And in general, if you take an arbitrary unfolding of a chain, there's no hope. You have no idea what's going to happen. Maybe the shapes will intersect each other. Your motion could be annoying. But the Carpenter's rule theorem tells us not only is there a motion, there's a nice motion that's expansive. And it turns out, as long as you have an expansive motion, of what I call the underlying chain, then that motion will not cause any of the pieces to intersect. Assuming they don't initially, then that non-intersection will be preserved, provided your adornments are slender. So that means if we have some slender chain, slenderly adorned chain, let's say open chain, then via an expansive motion, which we know exists, you'll be able to unfold the chain straight. And then if you want to go somewhere else, you can unfold that out somewhere else straight and then glue those motions together, and you get your motion from A to B. All right, let me start with sort of an intuitive proof. Suppose you have two slender shapes that are touching. When they're touching, suppose you're moving around. Eventually, if they're going to cross, first they have to touch. So consider the moment at which they touch. I claim they can't cross from there. And the intuition is the following. Take an inward normal from, when they touch like this, they have a common tangent. And so if you take the inward normal on both sides, those inward normals are collinear. Okay, and you know from the second definition, I didn't prove they're all equivalent, but they are, that we will get some points on the bars, on the edges, on the bases. So what? Well, if I take two bars, and I'm computing expansive motions, meaning I know this distance increases, this distance increases, this distance increases, and this distance increases. Those are the struts that we added. It turns out, I've actually used this once before, I think, that in fact, if you take any 2 points on the bars, that distance also has to increase. It's pretty obvious because these are straight things. If any point here was going to approach any point here, you would need to either move this point closer to this edge or this point closer to this edge. And if you move a point closer to an edge, one of these two edges will get shorter, and that's not allowed. So if all four of those cross distances increase, then in fact, distance between any 2 points on the segment increase or stay the same. Remember, in general, we're expansive. There are some pairs that you cannot strictly increase the distances of, although most of them we can. And so that's good news. If this distance increases, it's pretty hard for them to start intersecting there. This is an intuition, not quite a proof. You can make this into a formal proof. It's just messy. Trouble is, for example, if the distance stays the same, you can kind of spin around that point. You can move first order left or right. Maybe it's not actually this point from this guy and this point from this guy who are going to start penetrating, because as you move, maybe it's some point nearby that falls inside. It's a little tricky to see who exactly can intersect what. It looks good. And in particular, if this distance is strictly increasing, then pretty much has to move away. But there's a lot of subtle details, and it's kind of a mess. We did it once. But in fact, we found a simpler proof that does not have to rely on this. But I still like this from an intuitive standpoint. It's kind of clear why that inward normal property is good. If the inward normals hit outside the bar, then you have no idea whether that distance expands. As long as it hits inside, you're golden. So let's start with a special case that's really easy to prove. It's easy to prove by appealing to fancy mathematics, though actually pretty old mathematics from 1934. There wasn't a lot of math then, and yet some great results. So let's start with the symmetric case, where you have your base, you have some slender adornment, and you have exactly the reflection of the slender adornment drawn below it. So it's reflectionally symmetric about that line. That's nice because instead of having to worry about half lenses, I can worry about entire lenses. Just like a special case. Every time I have some lens like this one, it's going to look like that. Circle centered here, circle centered here. That would be the half lens. I have, in fact, the entire lens. So really it's, if this shape is going to intersect some other shape, then there's got to be some lens over here that's going to intersect some other lens. So really I can just think of a single lens, pretty much, worry about one lens hitting another. Okay, in the symmetric case, it turns out, what do I want to say? This preserves non-intersection. Turns out not only is non-intersection preserved under continuous motions, which is what we care about, it's preserved for what I'll call instantaneous motions. In the origami context, we would call these folded states. We don't worry about how you got there. You just draw it again differently. It's like you instantaneously jump to that point. So in terms of configuration spaces, we have some big configuration space. And we say, well, ideally, I go somewhere by a motion, but maybe I just jump over to another point. I just redraw these symmetric slender adornments. I should say the motion should still be expansive in the sense that if you measure the distance between two vertices in the original, and you measure the distance between them in the final, in the new resulting configuration, the distance only goes up. It could stay the same or strictly increase. So this is kind of crazy. You don't even need continuity for this to hold in the symmetric case. So, in general, we're worried about some lens a lens is going to be symmetric about this line, but not necessarily about this line. We're worried about it intersecting some other lens. When could that happen? Well, here's a cool theorem. And this theorem has sort of come into fashion in the last few years. Actually, let me tell you a bigger result called the Kneser-Poulsen conjecture. It's conjectured I don't know how many years ago. It's also called pushing disks together. I have a bunch of disks in the plane. Suppose they overlap, who knows what happens, but a bunch of disks. And then I push them all together, meaning the opposite of expansion. All the centers of the disks get closer to each other. Is it the case that the area of the union or the intersection, all these things should go down? Seems intuitive enough, but was unsolved until 2002. Okay, somewhat recent. A special case of that turns out to be all we need. There's obviously disks lying around here. This is the intersection of two disks, so it seems useful. Overall, there's 4 disks involved here. There's one here, one here, one here, and one here. What we really care about are 4-way intersections between all 4 of those disks. That would be bad. That would be the 2 lenses hitting each other. Remember, really, there's a bigger edge here. But if they're going to hit, some 2 lenses have to hit. And that special case is much older, 1934. And it says if we instantaneously translate, you can't really rotate disks, doesn't change much. Say we have n disks, and we instantaneously just move them around, and I'm going to state it in the expansive form. And suppose initially they have no intersection, meaning they have an empty n-way intersection. And we instantaneously translate to an expansive motion on the centers. then we'll still have an empty n-way intersection. Now, in our case, we care about n equals 4. We have 4 disks we care about. We somehow move them so that the centers are the vertices of my chain. Don't even need that lemma about other points. I know the centers of my lenses are my endpoints. I know all those distances are increasing somehow. And now I'm even thinking about the instantaneous case. I just pick up all those points, drop them down, so all the distances increase. Then the theorem is if those 4 disks didn't intersect before, they still won't intersect. Therefore, the lenses don't hit each other, ever. Even when you can pick things up and drop them back down. Done. That covers what we need. Now, I didn't prove this theorem. I don't think it's too hard, but it's sort of not folding related, so I'm just going to take it as given. Okay. But that was just one special case. That's when we had lenses instead of half lenses. In reality, we have half lenses. So there's a little bit more work to do. Well, if this slender chain is going to intersect itself by some expansive motion, by the way, the general case, you need a continuous motion. It doesn't work anymore when you do it instantaneously. I have a nasty example here. I mean, sort of an annoying example. Suppose you take a bar and you take the Rayleigh triangle or just something really big, whatever. And you have another bar here with no adornment. And now I instantaneously move it to the configuration where I have the same, this guy didn't move. I just put this guy here, something. So, of course, if I measure this distance, it increased. But it's now self-intersecting. Okay, so if you pick things up and drop them down, it doesn't work in the general case. It's because this wasn't symmetric. If it was symmetric, then this guy was already intersecting. But we can nonetheless prove for the case we care about, which is continuous motion, we can, because we know there's a continuous expansive motion, we can still prove that no 2 half lenses will intersect. So now I worry about 2 half lenses intersecting. A half lens looks something like this. Oh, sorry, that's a lens. Half lens looks like that. Okay, it has 3 sides in general. This one's bounded by a disk, this one's bounded by a disk, this one's bounded by a base segment. So there's basically a bunch of cases you could worry about. You could worry about 2 of these guys hitting in the curvy parts. So that's case 1. That we get, what did I call them? The base. Well, I'm going to rename this because I don't like the terminology I'm using here. Curvy. Okay, there's the 2 straight sides, then there's the 2 of each, and then there's the 4 curvy sides. Suppose they hit on the curvy side, a curvy side of both. Well, if they hit on the curvy side of both, this is a convex region. I could actually just put back the rest of the half lens here and the rest of the half lens here. They still won't intersect because the bases are pointing away from the intersection. So this is actually covered by the case we just did. We know that if we can complete it to a lens and still not have intersection, maybe it intersects other parts, but we know these guys could not intersect each other because these entire lenses couldn't intersect each other. So case 1's done. Case 2 is about as easy. It could be we have curvy part meeting a base. So we have this example again, but now we try to intersect with the base of some other half lens. What should I do here? Anything useful I can do? Yeah?
Think about the points on that line as they should be expansive.
Yeah, these points are expansive from here.
Tiny lenses.
Tiny lenses, good, good. Screw this lens. Yeah, I mean that lens really does not participate in this intersection, right? Think of this as if there was no adornment there, which is like you have lots of tiny half lenses there, but there's just none. It's an empty union of lenses. This is obviously a slender adornment. There's no adornment. Okay? If the original was going to intersect, this should also intersect. And this one I can actually extend and make it a full lens because I'm intersecting on the top side here. These can't hit each other by convexity. Great. So this is a symmetric lens. This is a lens. This is a lens. Symmetric case. So we already know those guys can't intersect each other. We have, in some sense, there is a tiny lens here, which is from that circle and that circle. And the point is, the four circles defining those two lenses cannot intersect. So again, we're done by the symmetric case. The last case is actually, I guess, the easiest one. Base to base. Base to base is like this. And yeah, there's some adornments, but the adornments don't really play a role. So you could imagine erasing them and just talking about the tiny things again. But really, this follows just because the linkage is expansive. We already know that the linkage will not self-intersect itself. In particular, this distance is increasing and this distance is increasing. It's got to move away. So that can't happen. It could actually never get to the touching point if it started non-touching. Done. This proves that if you have a slender adorned chain, you take an expansive motion, you'll preserve non-self-intersection. If you have an open chain of slender adornments, this is great because you can straighten out your chain. Why don't I draw the picture? If you want to get from one shape to some other drawing of that same polyline, pretend all the lengths are the same and pretend there's all these slender adornments that are the same, you can straighten out each one and then just play this motion backwards and take this motion to here, this motion to here. This is something I call the FedEx algorithm. We're talking about it in the problem session because the original idea of FedEx is you send all packages to one central FedEx location and then send them out to where you want to go. Crazy idea, but it worked for quite a while. It's a little more complicated now, but still that spirit is there. And someone was asking in the problem session, well, what if you send a package from one point in California to and your neighbor? It's like, well, yeah, then it goes far away and comes back. But for math, it's no problem, no energy issue. So this is great for open chains. It does not work for closed chains because closed chains, there's more than one convex configuration. I could take that. I could take something more squashed. Now, normally, this is fine. We haven't proved it, but for regular closed chains, you can actually get from every convex configuration every other. Maybe we'll prove that in the polyhedra section because it's easy to prove there. Believe that. But once you start adding adornments, it ain't possible. So for example, if I take this thing and I add some adornments that just kind of fill in all the space, this is not so slender. But you can even draw it with it being slender. There's no way I can go from here to here. Okay, that's not very convincing because there isn't even a configuration like that. Here's a more convincing one. Suppose you have a parallelogram and you have a right triangle and a right triangle. And now I want to go to here. If I was allowed an instantaneous motion, this would be fine. Even be expansive. None of the well, no, it's not expansive. This distance increases. Okay, that's why this theorem doesn't apply. But these are two convex configurations I can't get from one to the other. So for closed chains, this doesn't quite prove the configuration space is connected. You have to worry about the convex situations. For open chains, it does. Open problem. Are there any other adornments like slender ones? Or is slender the most you could hope for a general result? Is there some shape that is not slender such that no matter how you add them to a chain, you still have a theorem like this, that they never lock? I would guess slender is kind of the most you could hope for, but I'm not sure. One special case we can understand is the case of triangles. We know equilateral triangles are bad. We know right triangles are good. We know even more obtuse triangles are good because these are slender. What if I take a triangle that's slightly more than 90? Slightly less than 90 here. I know if I go all the way to 60, it's bad. But what about slightly less than 90? Also bad. This is not convincing yet. This is equilateral triangles. I've made a more complicated example here in order to get a couple of properties, but one of them is that all of the equilateral triangles are the same size. It's a little bit cooler. You have to imagine where the bars are. There's like a bar here and a bar here and so on. This is what it looks like when it's self-touching. And the reason I'm looking at that is I think, what if I shear this whole picture or scale it non-uniformly in y? So I make it taller. Shorter. I make it shorter first in this picture. I'm going to make it taller in a second. I've got to correct things, but all of these triangles now, the base is along here. This is the apex angle. So here I made the apex even smaller than 60, which is not the direction I cared about. But point is, this thing will stay locked no matter how you shear it. And so here I have a bunch of triangles where the apex angles, you can make them arbitrarily small. So even if no surprise, if I have a super pointy triangle, you're going to be able to lock them like this. But also if you go the other way and you make this a kind of a less than 60 or more than 60 angle, as long as it's less than 90, this will stay locked. And to give you some intuition, if it's less than 90, I can apply rule 1 here. Okay, but as soon as that angle reaches 90, this apex will be 90, and so then rule 1 does not apply here. Okay, I think it'll still apply on the other side, but it doesn't matter. You really need both sides to be acute for rule 1 to apply. Okay, this example is actually a little bit messy to prove that it's locked. You can apply the rules like down to here, but then you're not able to apply rules anymore. Actually, you can't even do it in the last one, I think. Just up to here. Because here I have a nice acute angle. Here I don't have an acute angle. It's kind of annoying. The best way I know to prove that this thing is locked is to compute an equilibrium stress that's positive or negative on all of the struts. Remember, there's little struts here saying that this guy has to move away from this corner. Or it could slide along the edges, but it can't go on the other side. So you could do that. It's kind of messy. I will prove to you a simpler example. We already did the first one, but here's another equilateral triangle example. Even fewer triangles, and also locked. This one you can't scale quite as nicely, but actually, I could give you a choice. Which proof would you like to see? The easy one or the hard one? Easy? Hard. One person for hard. Thanks, Harrison. All right, I like easy proofs. They're more exciting. Okay, first, the hard part is I have to draw the example. If you want to see the hard proof, it's in the lecture notes. I kept it in there. This should be the same as that, more or less. Imagine self-touching. We're going to prove that it's rigid, therefore any perturbation is strongly locked. What should I do? Apply rules. Yes, I like the rules. I live by the rules. And first rule of the rules is don't talk about the rules. Now we have rule 1 here. First rule of the rules is apply the rules. So we can apply rule 1 because this is acute, this is acute. Okay, now I have to redraw. I should really have one of these in the problem set. Applying rules is so much fun, and it's also easy to make mistakes. So that's a good problem set question. All right, these are not touching. I mean, I don't really have to fill these in. They're triangles. Of course they're rigid. But now these are fused together. Can I apply any more rules? I think so. Try not to cheat here. This looks like a rule 2, right? This is an acute angle, so it's fused together. I'm just going to redraw that as fused together. Any others? Guess that's it. Huh. Now I got to do something other than rules, darn it. Life is not so easy. I'm going to look at, this is divine inspiration here. Well, co-author inspiration, I suppose. I'm going to look at that convex 1, 2, 3, 4, 5 pentagon. It's convex. Okay, not strictly. There's a corner of angle 180. Actually, there's a couple ways to prove this. I could just look at this convex arm, open chain, on the edges of a convex polygon. Yeah, what's the right way to do this? Okay, I have a better argument. Turns out if you take a motion of a convex polygon, any motion must decrease at least 2 angles. And that's really hard to do here. You can't decrease this angle, or this angle, or this angle, or this angle, because you've got this stuff in the way. There's only one angle you could maybe decrease, but actually even that one's probably not going to work. And I have to decrease 2 of them. Contradiction. So there's no motion of this thing. It's like those tightly packed convex configurations. You can't move from here, just looking at the inside of this thing. The rest has all been rigidified. Well, I guess there's one vertex here, but once this is rigid, then this triangle is rigidly attached to these 3 triangles. So the whole thing is rigid. And therefore, from last lecture, it's strongly locked. Lecture notes say 1 angle. I should change it to 2, because I'm worried about this one. But 2 is also true. It also decreases at least 1 angle, but in particular, decreases 2 of them. Where's lecture notes? So it turns out, and this is something we'll prove later. This is theorem by Cauchy, like 1800s. If you have a convex polygon, you move it, at least 2 of the angles must decrease, and at least 2 of the angles must increase. In fact, well, there's all sorts of cool things you can prove, but that's slated for another lecture. We'll see that in the future. I want to move on to a different cool topic, which is hinge dissections. Any questions about locked, slender, or non-slender adornments? So for triangles, we have a tight answer. You need to be right or obtuse. In general, slender works. I don't know if other things work, but I guess not. All right. Oh, another open question. Locked squares. Now, if you have squares that are properly aligned, draw them very well. So if the base of the square is through the diagonal of the square, that's slender, so those can't lock. But if you allow the base edge to be along the side of a square, like this, I take unit squares in the plane, open question, are these locked? It's probably really easy. We just haven't worked hard enough in proving that these things are locked. So that's something we could work on the problem session. These are examples in this paper. Say we conjecture these are locked, so there's some work to do. Fun toy question. All right, hinge dissections. The idea here is if you look at one of these things adorned chains we've been thinking about, where you have solid blocks hinged together at points, and you think about the moving, okay, we've been thinking all about the moving and when you can move from shape A to shape B, or configuration A to configuration B. But in particular configurations where they're touching, you can imagine erasing those cuts. And on the top, I get a square, and the bottom here, I get an equilateral triangle. So we call this a hinge dissection from an equilateral triangle to a square. This one goes back over a century by this puzzle guy, Henry Ernest Dewdney. And natural question is, can you do this for any two polygons of the same area? You have to preserve area, because fusing cuts does not change the area. Natural question. We've been working on this question for about 10 years. We started in 1999. And the first thing we proved is that you couldn't do everything, but if you pixelate shapes, it works. So in this case, we're not pixelating. We're dividing our shape into half squares. It turns out if you take so here I have 32 half squares. In the letter A, I also have 32 half squares. So I want to go from the square to an A. Turns out if you take each of these half squares and replace it by, I guess, 4 smaller half squares, and I hinge the half squares in this particular pattern. You can check it. It alternates. It's in a very regular pattern. It will work that way in the square. It'll also work that way in the letter A. I don't actually know for sure whether there's a continuous motion between these two without self-intersection, because these are not slender adornments the way I've drawn them. But this is a hinge dissection that exists in all of these states, the whole alphabet and numbers. And it's just 128 pieces. So that would actually be really fun to animate. I haven't tried to do that yet. You can generalize that to 3 dimensions. I think I showed this in lecture 1. Here we have solid blocks. So this is like pixelating, but it's just stretched. And we have piano hinges, about 1,000 blocks here. And you can pick up your gloves and reconfigure this sculpture into whatever shape you want. Theorem is you can make it into any polycube, any shape made out of not 1,000, but 250 or 125, I guess. You divide by 8 to make a 2 by 2 by 2 larger square, or a larger cube. It's a stretched cube, but same thing. And then you can make any shape made out of those shapes. That was the beginning. This is not everything. It's everything up to some resolution. But we would really like everything. And in this class, 3 years ago, we proved you can make anything. I think I posed this question in the very first problem session 3 years ago, thinking, maybe we can prove some special cases, something interesting, and then like 2 or 3 problem sessions later, it started to collapse and get solved. Which is super exciting, given that we've been thinking about this for 10 years. So this is going to be a little more general than two polygons, as suggested by all those, like the alphabet. There's one hinge dissection that can fold into many different shapes, not just two. So you take any finite set of polygons of the same area, then there's one chain of polygons hinged together at points that can continuously fold into all of those things without self-intersection. Now, how do you think we're going to avoid self-intersection? Slender. Got this great tool lined up for proving the continuously part of this theorem. The other part requires totally new ideas, but continuously is going to be easy because the name of the game here is we're given polygons we want to make, but we can make them out of a chain of arbitrarily many pieces. So if we have some chain that is working without the continuity, we can cut those pieces into smaller parts until they're slender. Turns out that's going to be easy. I'll come back to that. The hard part is to do this with ignoring continuous motion. So there's this crazy idea, which comes from Zach Abel, who is attending the problem sessions this year, so a bunch of you know him. Let's say, right. I guess number 2 is the crazy idea. So hinge dissections are actually named after something else called dissections. With dissections, you don't care about hinging the pieces together. I take one shape, I cut it into a lot of parts, that's the dissecting. I rearrange the parts however I want, rigid motions, and then fuse together the edges, and I get another shape. So there's no hinging here, there's no folding. And it's well known since 1800s that dissections always exist. I can give you a quick idea of how that's proved. You take some polygon and some other polygon of equal area. Just triangulate both the polygons, because that always makes life easier. Still, nothing's really matching between these two. If you take a triangle, if you just cut halfway up from the base and then cut here, you can even do this hinged. You flip this around and flip this around. You get a rectangle of half the height of the triangle. This is like how you compute the area of a triangle, right? Very easy. So do that for each of these triangles. Just cut them so they make rectangles. Do that here, do that here. What you'll be left with is a whole bunch of rectangles here and a whole bunch of rectangles here. Still kind of a mess. But there's this crazy dissection, which I won't be able to draw, and I didn't bring a picture of it, that you can basically take a rectangle of some height and make it a rectangle of some other height. It's got to preserve area. So maybe it'll look something like that. There is a dissection from here to here. It's not hinged, but you can do it. Yeah. Believe me. This goes back, I don't know, 3 centuries or something. Once you can do that, you can take your pile of rectangles here and just change them all to have the same height. It's got to be smaller maybe than your original height. But you just pick some epsilon and make a whole bunch of rectangles of epsilon height. If you turn this into a rectangle of height epsilon, this into a rectangle of height epsilon, each of these into a rectangle of height epsilon, and then string them together, you get a super long rectangle of height epsilon. If you do the same thing over here, you will also get a super long rectangle of height epsilon of the same length because they have the same area overall. So I can dissect this into the rectangle, I can dissect this into the rectangle, now I just FedEx it. Except here FedExing means I take the cut pattern here, I overlay it with the cut pattern on the other, which could square the number of pieces. Tons of pieces in this thing, but it works. And you can get from any polygon to any polygon using those gadgets. What I want to focus on is the hinging. Hinging is where the action is. for us folders, and this was the open problem for a long time. So the crazy idea is hinge arbitrarily. Oh, that was 2 shapes. If you want K shapes, you just overlay K of those cut patterns. You'll get some collection of pieces that can be reassembled into your desired polygons, your target polygons here. Of course, not by hinging. And definitely not by hinging arbitrarily. It's like you pick a piece, you hinge it to any other piece you want. I don't care which piece. You just keep hinging all these pieces together. It's insane. How could this possibly work? Well, by steps 3 and 4. Only 2 steps to go. This is the crazy idea. For a long time, we tried to mimic this proof, but make all the steps hingeable. What's hard about that is even if one step is hingeable, like the triangle to a rectangle, you can't really combine 2 hingings. You can't FedEx. You can't do one thing and then the other. You don't have transitivity, because one hinging may not be compatible with the next hinging. So instead of trying to make it all work hinged all the way, we just let it not work and then fix it. Great idea. The way we're going to fix it is by subdividing the pieces, which will mean we have to add more hinges. And step 3 is do this to make it work. So in some sense, we know how we want to assemble the pieces. That's what the dissection tells us. That's what step 1 tells us. It said if you arrange the pieces like this, it'll give you the polygon you want. Somehow I want to make each of those assemblies valid. I'm going to do that one at a time. I'm going to enable the first one, then enable the second one, and so on. I could actually get one for free. Instead of hinging arbitrarily, I could hinge to make the first one right. I just draw it as they are and then just somehow add hinges to connect it all together. But I won't even worry about that. I'll just make it work for the first one, make it work for the second one. This is not going to be efficient. I should mention that. Not particularly efficient. Okay, the 4th step is make it slender. And we're going to use the same trick of subdividing. And that will solve that. Okay. Haven't said much yet. Now we have a plan. We need some gadgets. And here's where I get way beyond the pictures I could draw on the board. This I could draw on the board, but the picture to come I could not. So here's a general picture. Let's say we have some hinging in some arrangement. We really want it to be different. So we're committed to having a hinge here and committed to having a hinge here. We can never remove hinges, otherwise we'll break previous constructions. But what I can do is cut up the pieces and add more hinges. As long as it can still fold this way, I can still make everything I could make before. I just also want it to be able to fold into this. This does not look like a folding. Here I'm detaching the green thing from B and reattaching it to B prime on the top. So I just shifted the orange thing down and reattached the green at B prime instead of B at the same vertex A. This is not everything I need, but this will be really useful. If I could do this, I'll be able to do everything in like a couple steps. So let me show you how to do this. Watch. Okay, so this is the dissection. We're going to cut out a lot of little isosceles triangles in pairs here. It's basically slicing up this angle. So here 2 of them are still, or 2 pairs are still in, and 2 pairs have just been folded out. And then we're also, so remember we wanted to go from here to up there. So we're also going to cut matching little triangles along the edges, along some path that goes from this vertex to that vertex. There's always some outside path I can follow. And so I'm going to cut. Now, let's see. The way we do it, we're making very shallow triangles here. We have to make them, I want to make them match the triangles that I'm going to be cutting out here. So it's got to be an even number. I just want to divide up that edge into an even number of tiny pieces. And then these 2 match the size of those 2 pieces, and these 2 match the size of those 2. So that in particular, I could not touch anything, leave it the way it used to be, and I have exactly the old picture. But alternatively, and so it hinges all the ways it used to be able to hinge, but alternatively, I can take these pieces out and rearrange them like this. So the pieces are colored the same as they were before, except now instead of putting these green pieces in here, I put the green pieces along the boundary here. And we designed them to fit perfectly. So these two came from here. These two came from here. These two came from there. These two came from there. And if you think about it, then the green piece has reached around and can now touch there. We still have these orange pieces. They don't have their holes to go into before, but conveniently there are holes right there. And that orange chain is attached right at the top, right where it needs to be. So you just stuff them in. Never mind how you stuff them in. We don't have to worry about continuous motion yet. That'll come later. And there you go. So we've moved this green piece up to there. And it had to attach at the same vertex with the green piece. Now, this is not quite what I want. What I really like to be able to do is take a piece and move it anywhere I want and attach it at a different vertex than from before. Because in general, I just got to put that green piece somewhere. It's touching somebody because I want to make a connected polygon. But I might not want to attach it at the same vertex. I might need to turn it around and attach it to some other vertex. Turns out you just do this twice, and you can fix that. So this is the elaboration on step 3. And in general, we're going to maintain at all times the pieces are connected together in a tree. Ultimately, I want an open chain of hinged polygons. But I'll worry about that at the end. For now, let's take it to be a tree. So far, it looks like a chain, but easier to think about. A tree. And then the key thing that we are able to do, what this picture almost proves, there's another issue which I'll get to, is the ability to effectively move a rooted subtree to attach at another hinge, any other vertex. Okay, what I've drawn here is we're moving one piece. But of course, if there are more pieces attached to the green thing, they could come along for the ride, no problem. So in computer science, we call that a rooted subtree. So you have some collection of pieces. You have some tree of pieces hanging off. Basically, if we deleted this vertex in a tree, it would detach it to two parts. So here's part A, here's part B. And maybe I should actually give these names. So here, this is A, this is B, here's little a, and here's little b. And what I can do is pick some other point, A prime. This is a whole bunch of pieces. I can pick any vertex of any piece in A, and I can move B over to there. Just redraw it here. Here's A. Here's the old vertex, little a. Here's the new vertex, little a prime. And I can attach the triangle to be there, but it still had to attach at the same root, little b. What I'd really like to do, suppose I have some other vertex here, b prime. I'd really like to make b prime attach to a prime. This is step 1. Step 2 is to do the same thing, but with the roles of A and B reversed. This is a rooted subtree. It's everything at this root and below. But this is also a rooted subtree. It's everything at this root and above. So I'm going to take this thing, think of it as a rooted subtree, and say, well, I'd like to move this rooted subtree to attach it B prime instead of B. It's exactly the same operation, just reversing roles. Then I will have B with vertex little b prime. And then I have my blob A, where this is A prime, and this is little a. Okay, just rotating pieces. So look, I've now accomplished these two chunks of pieces, I've been able to move subtree B. Instead of attaching at little a, little b, it now attaches at a prime, b prime. This really means I can take any piece I want. You can think of B as just being a single piece, in fact. But I need this operation to work for subtrees. I take a single piece, I say, well, it's currently attached at this vertex to this vertex, but I really want something else. I want some other vertex of B to attach to some other vertex of any other piece. And this will let me do that. I pick the vertex I want to attach to, and I pick the vertex I want to attach from. I do 2 of these rooted subtree moves, these things, and then I achieve moving this piece to anywhere I want. Question?
So it seems like you're using up perimeter when you do each one of these. So
Yeah.
what happens if you need to use the same edge?
So question is, I'm using up perimeter. What if I had to use it again? Because I'm following one of these long paths, slicing up pieces like crazy. And now there's maybe some other piece that was attached to green and I want to move it somewhere else. It might have to follow along this path again. And indeed, I will. You can be smart about it. Or you could say, well, it'll kind of work. It's just now, just think about this picture. And you follow some path. There's now just more pieces you visit. So there's still an outer boundary to these pieces. I'm going to think of them still being in this state, not in this state. I can fix it to be whatever I want. And so I'm going to end up cutting this into little triangles and little triangles and little triangles. It's going to get really messy really quick. Every time I do one of these operations, I potentially double the number of pieces or worse. So this is going to be exponential number of pieces if I'm not careful. You can be careful and do a little bit better, but you cannot hope for a bound in terms of n. Like if I have, like I would hope for n to some polynomial in n number of pieces. That's not possible even for dissections. If I have a nice fat rectangle and I just say I want to make it into a super narrow, skinny rectangle of the same size, same area, that's going to require a lot of cuts, even though n is 4. So I can't hope for a polynomial bound. You can actually get a pseudo-polynomial bound in a certain sense. But I don't want to get into that. Let's go for existence. So that was a good question. We're going to use this parameter over and over. There's unfortunately another issue with this construction. This is not enough because here I basically assumed that this green piece was like one solid piece attached at one point to the orange. As soon as I do this operation, there's now a whole bunch of pieces here at this vertex. I have to do a more general thing. This is where it gets messy. Yeah, exactly. In general, I might have several hinges connecting several pieces over here to several pieces over there. Pieces that don't have hinges I don't care so much about, but I have to worry about this in the general case. It's messier. So this is the input. Our goal is to attach these 3 pieces, because this is like a rooted subtree here. I mean, initially this may have just been one piece, but it's going to get cut up pretty quickly. So I've got to deal with the case that there are these 3 pieces simulating one. Maybe there's other stuff hanging off. That's not a big deal. And I need to move this entire sort of bulk hinge somewhere else. Where are we going? It looks like the top. Little b prime. So here we're attached to B. We want to attach to B prime. It can be done. It's a little trickier because more things have to match up. So again, we're going to slice out from the corner of green, the corner of purple, the corner of yellow. But our pieces are going to look a little different. So for green, the first piece, we'll still make just skinny triangles. You can barely see them, but they are triangles. And they're again trying to match the edge lengths over here. So we're walking along the path, same path as before. So we just cut up a bunch of skinny triangles to make that work. But purple one, it's not going to work if we just did that for all of them. There just aren't enough slots to put things, because really you want to traverse that boundary 3 times. And here you can't just do it one at a time. It won't work. You'll get an infinite loop. So what we do is each of the little triangles that would have come out of here, we actually split into 2 parts. Maybe easiest to see on the yellow. There's a triangle, and then there's this non-convex quadrilateral. a little kite. It just sort of fits on top of the triangle. If you glue them together, you get a regular old triangle, and it fits in here just like before. Okay, but I take that triangle, I cut it into two parts. I do that for both purple and yellow. But notice this yellow triangle is bigger than this purple triangle. A little bit. How much bigger? Well, it's designed so that this yellow triangle is the same size as these two pieces put together. And this triangle is the same size as this piece put together with itself. Okay, in general, the triangle at the next level up will be the same size as the two pieces from the previous level. Except here there's only one. Okay, why? Because we want to do this so that they all fit. If you take just the quad parts of everybody and the triangle of the last guy, then that triangle will fit into the quad of the next one, which will fit into the quad of the next one perfectly. Because as far as this yellow quad is concerned, that purple plus green is the same size. Purple plus green is the same size as purple plus purple, which is a regular triangle. This triangle is supposed to be the same size as that yellow triangle. So from the viewpoint of this yellow quad, it just wants a mate like this, which is the same as a mate like this, which is the same as a mate like this. And so those stack in, and they perfectly fit along. So the triangles we end up cutting out of the perimeter here are the biggest size. And then you can squeeze them all together like this, and boom, you get your alternate dissection. Oh, yeah. Then the other fun part, what you're left with is just the triangles from each of the colors, except the green. And conveniently, yeah, conveniently it just works. So there's a little more work to do, because you see there's also these red pieces. Where did those come from? Just more stuff. I see where they came from. Up there at C3, a little corner got cut out. Oh, it's such a mess. But the idea is, well, the purple triangles are the same size as the green triangles, so they can fit in the green piece and fill in these holes. And then, well, the yellow triangles are the same size as the purple triangles when you add them together. That's what we cut out of here. And so the yellow just fits in there and fills in this space. And so that, we just sort of shifted by one. The trouble is the yellow guys, we don't quite have enough. And for that, we cut out some corner up there just to fill them back in. So you could just stick the red thing back into the red vertex, nothing changes, or you can take the red guys, stick them into the yellow triangle. And in the end, we successfully move a rooted subtree from anywhere to anywhere. Lots of things to check here, but you stare at it enough, it works. And it works for any value of 3. Here we were talking about 3 pieces, 3 hinges, but you can do it for any count. That's the gadget. And good. We have just enough time to talk about slenderifying. So if we do this over and over, move each piece to wherever you want, move all the pieces to where you want for a target shape, then do it for the next target shape, then do it for the next. You'll still be able to go to all the old foldings, but you can also go to the new ones. The last step is, how do we subdivide to make our thing slender? And so we have some tree hinging. It's not a chain. We want to also make it a chain and make it slender, because slender only works if it's a chain, not a tree. So we have some tree of pieces here. I've drawn 2 pieces to make it a little simpler. But this really works for anything. It's super simple. Triangulate the pieces, just because triangles are easier to think about. Then for each triangle, cut to its centroid, this where you can fit the largest disk. If you do that, each of these 3 angles will be obtuse. So as long as that's the apex of the triangle and this is the base, those are the base edges, that will be slender, because that's obtuse. Or it might be 90 degrees, maybe. Maybe not even that. I think it's always strictly obtuse. So you do that for each of the triangles, and then you just sort of walk around the outside boundary and say, well, just hinge things together in that order. So I'm going to have this triangle hinge to this one, hinge up there, around. So I just walked around the outside boundary. Now the key thing to check is that every hinge that was here still exists here. It's still possible to fold there. And we just got more hinges, no big deal. Just like before, the constructions we've been doing, we've been cutting up the pieces, adding hinges, but preserving all the old hinges. Therefore, any motion that was possible before is still possible. And furthermore, this is now a slenderly adorned chain, so we know that it's configured open chain. We know its configuration space is connected. So all those things that we knew could exist, it could be like this, or it could instantaneously move to here. Now we know there's actually continuous motion from everywhere to everywhere. And this is kind of a fun culmination of all this linkage stuff. With Carpenter's rule, with slender adornments, all these powerful tools, we build up universal hinge dissections, basically transformers that can fold from any, in this case, 2D shape to any other collection of 2D shapes you want of equal area. And again, you can generalize it to 3D, although this will work. Any dissection you have in 3D will be hingeable. But dissections get a little bit harder. You need not just that the volumes are the same, but something else called the Den invariant is the same, which is I don't want to get into. That's hinge dissections. Any questions? All right. Turn in your problem set.